to the Isaac Newton Institute for Mathematical Sciences. My name is Christy and I'm the Deputy Director here. We are truly delighted to be hosting this special event as part of the Cambridge Science Week on Murderous Mathematics with Kjartan Poskitt. Mathematics and magic have a long standing history, and indeed the magic square, which I'm sure is known to very many of you, was known to the Chinese as early as 650 BC. Before I introduce our speaker, let me tell you a little bit about the Institute, and first get a couple of practical matters out of the way. First of all, there are a lot of you in here. Fire alarm. If the fire alarm goes off, this is not a practice. There's no practice to be here. Please vacate the building as quickly as possible and vacate in the congregate in the car park over there. And the second thing is mobile phones. Even in standby mode, mobile phones interfere with our audiovisual equipment and will cause a buzzing sound that will be streamed live to the world and recorded for posterity. So please switch off all mobile phones now. So based in Cambridge, the Newton Institute is a national facility that supports mathematical research throughout the UK. And although its role is a national one, it receives very significant support from the University of Cambridge, for which we're truly grateful. However, we also rely heavily on donations. So if any of you would like to support the Institute, please go to our website to find out further details. Now, we may be biased, but we think that this is a very special building. The Institute is part of CMS, Cambridge's Centre for Mathematical Sciences, and many of you who know this area might have noticed on your way in the core building, which has a lawn on its roof and even daffodils at this time of year. This building was purpose-built with a creative space designed to nurture both individual and collaborative research, and it has 140 square metres of blackboards in the building. You might have noticed also at the moment we have on display in the lobby a Turing machine. Do take time to have a look at that on your way out. A landmark in the history of the Institute was the announcement in this very room by Sir Andrew Wiles of his strategy for solving Fermat's last theorem, which had been a problem which was an open question in number theory for over 350 years. But now, without further ado, I'd really like to introduce our speaker. We are delighted today to welcome Kjartan Poskitt. He is a television presenter, a best-selling author. His numerous books include the Murderous Mathematics collection, as well as the Agatha Parrott series. Kjartan, over to you. Thank you very much.
All the way down from York this morning. This is the toughest bit. Right, there we are. How lovely to see you all. I was here 10 years ago because it's the 10th anniversary of the building. Every 10 years they ask me back. There we go. Isn't that fantastic? Yep. I'm Kjartan. I write the Murderous Maths books, but when I was a young person like you, I wasn't actually going to be an author. I was going to be a rock star. That's what I was going to be. Goodness knows where that went wrong, but thank goodness it did. Right. Usually when I do a Murderous Maths talk, I start off by saying that my book's full of the horrible histories and horrible science books, yeah? And normally I talk about a few murderous mathematicians, people like Pythagoras. He was a nutter. He was a very clever bloke, but he killed people, yeah, and Thales and people. But today, as we're in the Isaac Newton place, I'm going to talk about Isaac Newton. Can we possibly lose these two fluorescents at the top here? Is that possible? Sarah? Come on. Oh, who did that? That was good. Someone's listening. That's great. Anyway. So what I've done is just done a little rush through what Isaac Newton did for us, okay? He was a very strange, in many ways disturbed bloke, but possibly the cleverest guy that has ever graced this planet. So there we are, this is Murderous Maths. I was asked it was about 12 years ago, I just started writing the Murderous Maths books. I was asked to write a book about Isaac Newton, and I thought, what's to write about? Bloke sits in the field, apple hits him on the head, end of story. Turns out there's a bit more to it than that. The other thing I remember from last year, 10 years ago, is the disparity of brain power sitting in front of me. Some people are sitting there. Where's my little friend who's 8 months old? There's a lovely little girl when I came in. I can't remember where she is now. Is it Annabelle? Where is she? Anyway, I've got a little friend there. There she is. Now, she's the clever one. Try and keep up. all right? But, so I'm keeping this reasonably simple for the young people at the front. You people at the back who want to ask, really complicated questions, you can ask all your life. Right, there's the Isaac Newton book. That was its new cover. So ladies and gentlemen, proudly to present Isaac, okay? This is a little crash through his life and what he did for us, right? Isaac Newton, he was born of all days on Christmas Day in 1642, and at the age of 12, he went to school in Grantham. He was born just outside Grantham. Age of 12, went to school in Grantham. What are you laughing at? It's all right, keep going. No, they didn't. It's going to be a long afternoon, isn't it? There we go. He had quite a difficult upbringing in many ways. He was bullied at school. He wasn't very good at his lessons, but something inside him snapped. The first thing he did was he beat up the school bully. Allegedly, he grabbed the guy and rubbed his face against the church wall. Whoa. And then he said, I'm going to come top in everything. Nobody is ever going to bully me in my life. Nobody is ever going to say I am wrong. And that driving force is what propelled him to do what he did. He went to Cambridge, Trinity College, just over the river there at age 18. While he was at Cambridge, this is the sort of stuff he was learning, and he worked 18 hours a day. Maths, languages, nature, the Bible, alchemy. We don't do it in schools these days, more's the pity, because alchemy was a rather good mixture of sort of chemistry and witchcraft. They were trying to do all sorts of strange stuff. But old alchemists were trying to turn lead into gold and things. Isaac was a bit more advanced than that, but it was still a very strange science. It was also bordering on the illegal, okay? Because everybody's very religious in those days, but Isaac Newton wasn't very happy with the way they'd interpreted the Bible, and if he'd actually spoken out about it, he could have got into big trouble. So he kept a lot of what he did very secret. I don't know about the crocodile, it's just a good picture, had a crocodile. I don't know if he had a crocodile, don't care, crocodile. We love the crocodile, okay. As well as that lot, he also studied light, philosophy, more maths, more Bible, and astronomy. Now, a few years before Isaac was born, there have been some massive breakthroughs in people working out how things moved around the sun, the earth, the planets and things. The religious people who were in charge said Earth is the centre of everything and everything moves around the earth. But about 200-300 years building up to Isaac Newton, people had started to think differently. It was very dangerous to think differently because people thought you were a heretic. Nasty things could happen to you. One guy in particular, Johann Kepler, this guy came up with something which I think is just absolute genius. He worked out that as a planet goes around a star or a sun, whatever you like, just by looking at these tiny little dots in the sky and measuring and identifying what was going on. First of all, he worked out that they don't go around in a circle, they go around in an ellipse shape. More importantly, when they're closer to the sun, they go faster. And this diagram explains it. Supposing it takes a month to go all the way from there to there. When the planet gets further round, it will take a month just to go that small distance, okay? The idea being is that when they're further away, the planets move slower. But this is the most amazing thing he worked out. He worked out that if you plot the area, so supposing you've got your planet there and you draw a line from the planet there and then move it up there, it gets better in a minute, honest love, don't panic. Is she okay? Are you right, Mummy? I'm not troubled by them, I'm sure nobody else is. This area here, as the planet moves in a month, is equal to the area here mapped out there. How he worked out the fact these two areas would be equal, but that was his governing law to tell you how fast the planet moved and how the speed changed. That diagram comes up a lot. Right, Isaac, let's get it all in and let's see what Isaac did for us. I hope you're liking this stuff. Anybody here remember Monty Python? Yes. Yeah. About 2 years ago, I found you could do Monty Python cartoons on PowerPoint. My life changed. I don't think I've actually had a proper meal or had a sort of evening in front of the telly for years now. I'm sitting there doing my PowerPoint. Right, then here we go. What did Isaac come up with? At the age of 23, it got to 1665, and he came up with the most extraordinary bunch of sort of discoveries. Any one of these would be enough to make you remembered and famous. He came up with about 6 or 7 of them in the space of about a year. Now remember, at the time, people didn't know much about anything. Isaac was studying the movements of planets and stars and everything else. Some of the sums in complicated were terribly complicated, the sums. Lots of little fractions and powers and roots. There were no calculators. They'd only just invented decimal fractions. They'd only just invented things like log tables. they needed a better way to work the sums out, and so he worked out a nice quick shortcut. Here we go, the binomial theorem. So all right, laughing, this was good stuff in those days. Isaac Newton used to work out calculations to 50 places of decimals. That's how meticulous he was. That was February 1665. Moving on, May 1665, they were trying to study what happened when things went round corners. Nobody could ever quite analyse it. The best they could do was draw like straight lines, turn the curve into straight lines, and of course the more straight lines you put in, the closer to the curve you get. What Isaac Newton did, he worked out that any instant, doesn't matter what kind of a path you're moving, at any tiny instant you are actually moving in a straight line, just that the straight line turns. I know this all sounds a bit obvious or a bit what's the point, but it does come up in a minute. And tangents, he works out that if you're going along a curved path, at any instant the direction you're travelling in is the tangent to the path. Don't worry about these diagrams if you don't understand them. It's just that at the time, this again was a huge breakthrough in analysing how things moved. But then something rather strange turned up. It was the Great Plague. Kicked off in London. Where's London? Whee! And it spread. It didn't just start in the East End docks. It started to move across the country and it started to hit Cambridge. Isaac did not want the plague. That's not a real picture, that's what I made up, because he never caught it. Because quite sensibly, Isaac moved back to Grantham. When he moved back to Grantham, the story goes, he was sitting under a tree with an apple on it. I'll say the story goes, I'll tell you the story, and then I'll tell you what's wrong with it. Okay? He was sitting there, minding his own business, and this happened. Now, if it had happened to me, the chances are, I'd have done this. Where's it gone? However, Isaac Newton, you're the only people ever going to get to see this, I'm glad you're laughing. Isaac, theoretically, started thinking very hard about this. He said, there's the apple, fell down from the tree. Why did the apple fall? More to the point, there's other things up in the sky, such as your actual moon. How come the apple fell down, but the moon didn't fall? This is how Isaac justified his thinking. He said, okay, let's think again. There's your Earth, there's your apple, you know, a short distance above Earth. Much higher up is the moon. Supposing the apple was as high as the moon, would the apple fall to Earth? Answer, yes, why not? Why doesn't the moon fall to Earth? Then he realised it doesn't fall to Earth because the moon is going round. The apple's basically stationary, falls down. But the moon going on, you know this, if you get a bucket of water on a piece of string, don't try this at home, children, but if you wave it round like that fast enough, the water will not come out. You know that? Yeah. Some little kids going down here going, oh. Don't do it at home. Don't say the weird bald man from York told me to trash the kitchen, I'll be in trouble. So he thought, as the thing's going round, what happens is it's trying to escape, it's trying to get away all the time. If there's nothing holding it, it's going to fly off. However, let's bring the moon back. There's the moon. It's flying around. Something must be holding the moon in place. As long as that moon is flying around, there is a force pushing the moon away. There must be another force balancing it. And that force, what is it called? Gravity. It's that same force that pulled the apple down to the ground. Supposing the moon stopped flying around in a circle, it would stop trying to push away from the Earth, and the moon would fall down, just like that, okay? And if the moon fell down, it would hurt. So there you go. He started to get these thoughts about gravity affecting not only things here, but things up in space. He was starting to open his mind much further than people's minds have been opened before. So there we go, he's hit gravity. He's now thinking about this diagram here. He's desperate to think gravity is holding the planet to the sun or the moon to the planet, but gravity is affecting how that thing flies. He needs to really, really analyse the curve that thing flies in, and he came up with calculus. Sort of thing people start learning when they're 16, 17, 8. Guy down here went, wow, calculus, I love it. These guys, I'm 8 and I love calculus. Oh, good man, good man. There we are. What calculus is, when you get like a little diagram, and this kind of graph thing had only been invented just before Isaac was born. Descartes came up with this way of plotting curves. He worked out these tangents he worked out a way that you can find out the tangent at any point on the curve and also how the tangent changes using this thing. It's called calculus. That was a massive breakthrough. It's like learning everybody's PIN number in the world at once. It was huge, okay? He got the calculus. At the same time, by the way, somebody over in Germany thought they invented it at the same time. They've been rowing about it ever since. But for the sake of being in the Isaac Newton building, I'm going to say that Isaac won. Don't want to pick a fight here. And then colours. He was doing all sorts of strange experiments outside of gravity and sums. And one experiment wasn't very nice. Isaac was fascinated by light and what happened. He was fascinated by everything. But one thing, in the old days, they said how to make colours. To make red, mix a lot of white with a little bit of darkness, and that makes red. To make blue, mix a little bit of white with a big dose of darkness. Well, this is fair old rubbish. We know it is now, but then people believe that. We can prove it's rubbish, though. If I get a bit of paper, where are we? With sort of if I had something with printing on it, and had black and white printing, if I held it back, away from you, so that the colours merged, you wouldn't see blue, you'd see grey. It doesn't work. Isaac was the first person to think, no, this can't be right, this. So, he wanted to do some experiments. He did some pretty nasty experiments, but he wanted to experiment on flexible lenses, lenses that can bend. They hadn't got plastics in those days, and the only flexible lenses he could think of were the lenses in his own eyes. You're all sitting there going, don't go there. I'm going there. Here we are. What he did was he shut the curtains in his room. His curtains, by the way, were all dyed red at this point. He went completely mad. He shared rooms with a bloke called Wickens in Cambridge. And one morning, Wickens came back to find that Isaac decided to dye everything crimson. Suddenly decided it's his favourite colour. All the carpets, the cushions, the curtains, a lot. And when you think that the crimson dye is made out of sheep's blood, he's living with this guy. Can you imagine sharing a room with a guy and you come back and the guy says, I've covered everything in sheep's blood. Murderous Maths, I love it. He shut the curtain until there was a tiny chink of light going through. He then covered up one eye and stared at it to see what it looked like. Don't ever do that, you'll burn your eye out. He blinded himself in that eye for 3 days, but when it recovered, that wasn't going to stop him. The guy was absolutely obsessed. He then did something even nastier. What he did was he got a stick with a point on the end of it, and this is real film. Brace yourselves, here we go. Oh. And he discovered something. It hurts! Don't do it! No. Actually, by bending the lenses in his eye, he started to see interference patterns with the light. And these interference patterns can now be produced in much easier ways in the lab, but they're known as Newton's rings. And from that, he started to get an idea about light and waveforms and how it all worked. And then he went ahead to do another experiment, which is probably much better known. He got a triangular prism of glass. It's like a Toblerone made out of glass, yeah? And he shone a white beam through it, and this was the breakthrough. Suddenly, the white beam produced all the colours of the rainbow. Okay? Now, this is the first time anybody had sort of thought white can produce all the colours of the rainbow. Just a minute. What happens to red there? What happens if you shine red backwards? Will you get white again? And he took the individual bits of colour, he'd separate them off and try and shine them back through the prism. But once it was red light, it was red, he couldn't change it. He had proved that, in fact, white is made of all the colours. This is one of the first things he ever showed publicly. A few of his maths things he showed close friends, but this, nobody could call him wrong. He said, look at that, I've got that, you cannot call me wrong. And suddenly, this is one of the breakthroughs personally for him. People were starting to think, this guy is good, he knows what he's doing. Okay, he then got back to thinking about his planets, always thinking about the planets, and if calculus wasn't enough, he came up with integral calculus. There we are, he's got his little curve there, he's already worked out the gradient on the curve. What was also important was to work out these areas on this diagram. Integral calculus works out the area under the curve, again an amazing mathematical shortcut. They'll be doing it in primary school soon, so there we are. That was integral calculus, and then he came up with an absolute belt. It was about 2 years later. They'd spent a lot of time staring at space, analysing things. he came up with a fantastic new improvement on telescopes. Everybody had been studying the stars, and that's the moon there, using what they call refracting telescopes. Telescopes with glass lenses. This silly diagram here has only got 2 lenses, but some of these telescopes had 10 or 11 lenses in a great big long line to try and see these distant things in the sky. But there was a problem. The idea was the light from your thing, your moon, whatever it is, goes through the telescope and then you can see what's going on. But it doesn't happen quite like that. Because Isaac had found out with his glass prism that when you pass light through a thing like that, the light splits and separates. In fact, what really happens with these telescopes is as the white light hits that lens, it splits into the different colours. And just to show you the blue and the red colours, they actually focus at different points. You can't see the whole image perfectly. So rather than seeing a nice clear image, this is what tends to happen. It's not a very good picture, but it's fuzzier, which is no good to Isaac Newton. How could you make a telescope that didn't use glass lenses? And he came up with this absolute piece of genius. He got a bit of tube, a bit like a drain pipe. He put a curved mirror in the end, that is a mirror. And then here he put like a little, teeny weeny little zigzag mirror. He put another tube up at the top. Then he went to have a look inside. Wait! What happens here is the light comes in, bounces off the curved mirror, bounces off the little mirror, and focuses perfectly. But at no point does the light go through a piece of glass. The light is not bent or distorted. Now, when I first saw that diagram, and it wasn't long ago, I thought surely when you look through that telescope and you're looking down there and it reflects, you're going to see that little mirror in the way. It doesn't. The reason is this mirror is focused right the way out here. It's not focused at that little mirror. And to show you what I mean, if you want to look at me and hold your finger like that, you can still see the whole of me if you hold your arm out, can't you? Don't shut your eyes, keep both eyes open. You can still see the whole of me. But then if you look at your finger, you can see your finger. But if you look at me, you can see the whole of me. That's because you're managing to look past your finger. That's effectively what this mirror does. That's why it works. This was massive. He took this toy to show all the posh people, including the king, and everybody went, this guy is good at what he does. Because, again, his personal life is very difficult, but this was making it better and better and better for him. These little toys like this. He finally got a decent picture of the moon. I won't go into the personal life. I haven't really got the time. It was very nasty, very awkward. He made a lot of enemies. Thankfully, he also had 2 or 3 extremely good friends who supported him through a lot of troubles. But almost 20 years later, he produced possibly the most famous book in the whole of science, the Philosophiae Naturalis Principia Mathematica. What was this about? And it was mainly about forces. As I was walking down here today, I walked past, I don't know if I can see him here, but a gentleman with a little lad, and they were talking about forces and the inverse square law, and I thought, oh, I've got competition here we go. But for the people amongst us who just, find these things tricky, here are the basic, as simple as I can make it, what he laid down, the laws of motion. Number 1, everything stays still or keeps moving in a straight line unless a force acts on it. So at its simplest, that is going to stay still until you give it a shove. Have you understood it so far? Okay. Now, supposing there's no air resistance and there's no gravity, if you give that little ball a shove, it will just travel forever. It will move in a straight line. It will go right off the edge of the planet and go to the other side of space if nothing interferes with it, yeah? Supposing now we add just air resistance. There's still no gravity. If you give it a shove, eventually the force pushing against the air and the air pushing back will slow it down and it will stop. And of course, if you include gravity as well, if you give it another push, both forces will bring it to the ground. So everything stays still or moves in a straight line unless a force works on it. Number 2, this one is almost impossible to show on the pictures, but I'll try. Force equals mass times acceleration. This is absolutely fundamental. Anybody doing the GCSE physics will have to learn this. But at its absolute simplest, if you've got a little ball, give it a shove. Please. If you've got a bigger ball, give it the same shove. Slowly. It's actually more complicated than that. It's not the speed the thing goes at, it's how fast it speeds up. My car's broken down. I've got somebody in there steering it. I'm trying to push the thing. It takes ages to get speed up. If 3 other people give me a shove, we can get speed up much faster. That's because we can give 4 times as much force, and speeding up is the acceleration. Last one's nice and easy. For every action, there is an equal and opposite reaction. If I go like this, woohoo! My feet have put a force on the earth, and the earth has reacted by sending a force back, which has shot me in the air. Here's the really weird bit. I've shot up in the air about that far, but I've also put a similar force on the earth. The earth has shot downwards about that far. If anybody's got a copy of my book, Easy Questions, Evil Answers, one of the questions in it is, if everybody on earth got together and looked up and sneezed at the same time, would it be enough to blow the earth out of orbit? I have worked out the answer. Don't worry, we're safe. However, it all relies on, for every action there's an equal and opposite reaction. Nice little diagram here. We're going to get a great big ball now that weighs about as much as Isaac Newton, and we're going to put Isaac on roller skates. There we go. He gives it a shove, and this time when he gives it a shove, because there's nothing to sort of hold him back, this is what happens. There we are. Newton's laws of motion done with little cut-out cartoons. There we go then. We're just about to end of what talking about Newton, but I have to talk about the gravity formula because this encapsulates almost everything that he learnt together. This formula is vital. You get 2 lumps like this, and we call them masses, okay? There could be weights, there could be cannonballs, whatever you like, and you measure the distance between them, and here's it. He realised that everything in the universe is attracted to everything else by gravity, but he worked out the sums. This is where he'd been clever. A lot of people had suspected things like this. He had done the sums. All his many years looking down telescopes and working out his binomial theorem, he'd done the sums. He worked out the force between these things is you multiply the masses together, m1 times m2, multiplied by g, which is a tiny little number, then divide by the distance squared. It's what's called an inverse square law. But the nice thing about this, if you measure the mass in kilograms and the distance is measured in meters, and that is what that letter G equals, the force is measured in what we call newtons, and newtons are named after Isaac Newton, who came up with it. So there we are. Everything in the entire universe is attracted to everything else. These things are attracted to Isaac Newton, and if you let everything in free space just drift together, eventually everything will come together. You, me, the planets, the cars parked outside, the whole lot. There we are. First thing he understood, Teletubbies, I know. Now I'm online, good lad. So there we go, that is a very, very quick crash course on what did Isaac do for us. That was Isaac, now Sir Isaac Newton, born the 20th of December 1642, died 20th of March 1727, aged 84 years. I wish I had more time for him, but for the meantime, look at this. It took me ages to get this right. Thank you. Woo! Don't get up, I've got loads more yet. You better come up and say that was a lovely speech. I've got hours, girl, don't you worry and sit down there. My little friend, actually only 3, bless you. Hello, are you all right? Yeah, Mummy's saying don't be worried, the nasty man goes home soon. There we are. Right, this is my crib sheet. I'm looking at the clock now. We did start a bit late, so I intend, if you're all happy, to go until about 1:15. Is that all right with you people? If any of you have pre-booked things and you need to leave, I don't take offence, I don't mind, just toddle off, all right? I won't have a go at you. Well, might not. Risk it. Right, there we go. First thing I've got to show you is one of my favourite little tricks, Murderous Maths, because I worked out, as well as murderous people, maths is the only subject in which you can do magic tricks. And I love any sort of little magic trick. There you go, how about that? Come on! Yes! So what I need to do now, I need to borrow a volunteer. We're all going to do a little bit. Oh, here we go. They're going to the mad people at the front. Hello, mad person. We're going to borrow this man here. Here we go. Where shall we stand? I'm going to make a mess of these blackboards. I've been itching to do this since I got here. You stand about there for me, boss. Hold the smelly orange cloth. I'm going to go over here. I'm going to put some funny marks on this board. Oh, bad start. Sorry, man. Won't be asked back at me, breaking the chalk. I want everybody in the room, please, to think of a number in their heads, please, between 1 and 9. My friend here, what's your name?
Samuel.
Samuel, pick 3 people. If Sam picks you, shout out what number you're thinking of between 1 and 9. 5's good. Any different numbers? I've already got a 5. Pick somebody else now. 5, 3. Pick one of the old people. It wakes them up.
9.
5, 3 and 9's good for me. Thank you very much. 5, 3 and 9. Those are the numbers that you gave me. It's one of the best known tricks in maths. If you've seen it, forgive me, but you'll see where we're going. That's a minus sign, that's a plus sign, that's equals. These two are what I call turning around signs. If I get that number and turn it round, I get that. Okay, that's a minus sign. Quickly, all of you in your heads, 935, take away 539, the answer is 396. That's how good I am. Oh! Okay, we now turn round 396, all of you. What do I get? That's it. Finally, I add up these last two numbers. Before I do, Samuel, my friend, give me that piece of smelly cloth there. Okay, put that one there. Keep your hands together. When we're done this sum, I'm going to say show them the cloth. When I say show them the cloth, you've got to do this. Like that. I'm not kidding, son. No, you've got to do that. I'll tell you why. Listen. I could have been. Look, the answer to the sum is already on the cloth, but they won't be expecting that. What?
I know. I've seen this before.
You've seen it before? Well, what are you doing here? You should be up here. I could have been watching. Barney, where did it come from? These I've seen you before. Yeah. I'll get a police order about you. Listen, if you just go like this, if you just go, they're all going to just sit there and they're all going to go, it's a sad number. But if you go like this, they're going to go, Samuel, baby, who's seen it before? Woo! Yes! Go for it, Sam. 6 plus 3 makes? 9 plus 9? And there's a 1 to carry. 1 plus 6 plus 3? In your own time. We have an answer. 1089. Show them the cloth. Give that. Hold it up. Hold it up. Yes! Other way round. Like that. Give the man a clap. There we are. Thank you, Samuel. You go sit down, mate. Oh, good old Samuel. I'd like that. Are you all right, mate? Poor fella. I don't do dignity, as you probably gathered. Right. Can we knock these lights off again, please? 1089. I've known that trick since I was your age. What I didn't know is why it was orange cloth. It's to remind me to do the trick with the orange cloth. That's why I put that there. Why do you get the number 1089? There's two reasons. The first reason is I can prove it with algebra. Not going there. Oh dear, says binomial man. I love algebra. But he sat there with a face going, oh, my algebra. The other reason why we always get 1089 is because the number 1089 is weird. Now, I know what you're thinking. How can a number be weird? Most numbers are a bit boring, to be honest with you. 251, bit boring. 75,614,912, bit boring. 1089, hello. I'm sitting behind you on the bus. Get off! Yeah. I'm going to show you a couple of weird things about this number, okay? Before I do, I've got to ask you people, particularly the younger people, have you learnt your times tables?
Yes.
If you think times tables is a bit boring, a bit hard work, put your hand up and go, oh. Oh, and towards the back. And now if you think times tables is really interesting, put your hand up and go, I'm strange. Look at them all down there. That's what you get in this place, the strange people. I'm going to teach you your 1089 times table. It's going to take me 15 seconds, and you're going to remember this for the rest of your lives, whether you want to or not. Stand by for some seriously damaging incoming information. We're off. 1089 times by 1. Have a guess. You're good at what? Binomial man's going, don't really care, it's not clever. Times by 2, let's have a little look. 2178. Times by 3, 3267. Times by 4. Can anybody shout out what the first digit might be? 4. You're good. What's next digit? 3. You are good. What's next? 5. Oh, this is good. What's next? 6. Okay, times by 5. What's the first digit? 5. What's next? 4. What's next? Just a minute, there's a gentleman here on the front row. He's not saying anything. He thinks it's witchcraft. Man's sitting there going, No, there are one or two people who might not have got it. You have to spot the numbers going down. 9876. Give yourselves a little round of applause. That's all there is to it. There you are. You've learnt your 1089 times table. He did like that one. Now, 1089 is a weird number. Another weird number is the number 9. And if you multiply two weird numbers together, you get something slightly strange in the answer. Don't tell me about the columns coming down. Just tell me what's strange about this answer. Okay, first hand up. Oh, my friend.
It's the answer backwards.
It's the answer, yes, it's the number backwards, that's the one. 1089 times 9. And a lot of kids had their hands up for this. Not all the kids I talked to quite are as bright and observant as these kids here. I did Manchester Town Hall about 2 years ago, GCSE kids, aged about 16, all sitting there going, I didn't want to be born. I had 1,000 of them. I put this thing up there, and we were having fun. It was a bit of a sort of grind of a morning. I said, can you see what's strange about that answer? One kid, oh yeah! Oh yeah, oh look, yeah! I said, what's strange? It's turned orange! Whoa! If only it was that good, eh? I'll show you another one. If you get a big long calculator and you're putting 1 divided by 1089, if you look very carefully, you get all the numbers in the 9 times table in the decimal. Isn't that beautiful? But what's even nicer, when you see this one, you're going to applaud. Do you like that? Isn't that lovely? We like that. Now, I get people to send in facts too. Since I started writing the maths books, I've had emails from all over the world. Really, really nice, interesting, funny mixture of emails. And I get kids sending ideas in. Here's something you can put in your books. And I got kids to send in emails about strange numbers. Which piece of nice clean board can I ruin now? I'm going to go over here now, okay? And this kid sent in this one. For this one, do us a favour. Can you please count out loud for me how many little lines I'm drawing on the board? Are you ready? Go! 1, 2,
3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29.
If you don't clap that, you clap nothing. I got this email from a kid in Singapore saying, Dear Mr. Poskitt, did you know that 29 is the biggest number you can write out in the English language, and the number of little lines it takes to form the letters is the same as the number itself? So I sat down, I gave it a go. I couldn't make it work, you know. So I replied, Dear kid, get a life. No, I didn't say that. I said, Dear kid, I can't make it work. He said, if you do it yourself, you must put 3 lines in the letter Y. If you just put 2 lines in, it doesn't work. This makes it into a really cheap and nasty little childish trick. Who'd like to know it? I thought you would. What you do is you go back home tonight and find somebody who's not seen this trick, or at school next week. Get a bit of paper and you say, watch this, count the lines, and you write out 29. You don't have to do it in a funny order. You can do it this order, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. But remember, put 3 lines in the letter Y. When you've done it, you say, right, I bet you can't do that. They'll say, well, of course I can do it. I just saw you do it. Turn the bit of paper over so they can't see what you did. You can bet they will do the wrong sort of letter Y. It will only take them 28 lines. They won't sleep for a week. Isn't that beautiful? We like that one. While we're talking about kids that have sent me funny emails, there's something else I'd love to very dearly do here. I got a lovely email from a kid. They are interesting, some of the emails I get from young people. And it was, Dear Mr. Poskitt, what is your favourite net of a cube? I know, there's something not getting enough daylight, isn't it? But I thought, well, for those of us who aren't clear, that's a net of a cube, okay? It's made out of 6 squares, and no big surprises here, not rocket science. You can fold it to make a cube. Now, the weird thing is, you can't take any old shape with 6 squares and make a cube. For instance, this shape here, it's got 6 squares, but if I try and fold that into a cube, you find you can't stop it overlapping. You will always get a gap in the end of it. Nothing you can do about that. There are actually 11 different nets of a cube. I've got some shapes here. 3 people I need this time. I'm going to borrow a little lassie in the blue down there. Up you come, miss. Slightly scary looking kid down here. Yeah, up you come. There we go. 1, 2. Oh, no little hands up at the back. I hate to miss people at the back of the hand. Little lassie with the glasses over there. That's it, my lovely girl. Here we come. Up they all come. Look at this guy. He thinks he's Britain's Got Talent. He's Susan Boyle. I recognise you. Anyway, right.
I
Hello. Is it?
Yes.
Good. Right, okay. Now then, Well, I'll tell you what I'm going to do, I'm just going to sneak this table back a little bit because I want everybody else to see what these young people are doing. Watch out for the wire. Ooh. Actually, I've just realised after all this time, if I do that like that, everybody can see everything much better. It's blown up. Don't worry about that little trying to zap me one. Right, you come here. You three of you come and stand there and I'll try and manage this computer. You know, some people will be embarrassed at my lack of professionalism. Me, I just roll on, I don't care. Right, in you go. Are you back on? It's got the ump on now, hasn't it? Oh, there it is. There, well done, computer. Right, in a little line. You come and stand there for me, miss. You in the middle, my friend, and you at that end, my love, okay? Hello. Sitting there going, strange man. Right, there we are. Hold that one there. Don't fold it yet. Can you face the front, mate? Hold that one. Take one step backwards and hold that shape. Don't fold it yet. And you hold that one. Two of these shapes will make a cube. Hold them nice and high so the people at the back can see. Okay. Two of these shapes will make a cube. One doesn't. Which one doesn't? Who thinks the green one does not make a cube? Hands up, please. Ooh. Who thinks the blue one does not make a cube? Hands up, please. Who thinks the pink one doesn't make a cube? Hands up. Well, I'll tell you what. Let's just see what happens with the green one. Can you try and fold that green one to make a cube? Let's see if it's going to work. Oh, I'll tell you what, you made that look easy as well. Well done, my love. Perfectly done. Hold that one from me, hold it like an egg. It's one of these two. It's either the blue one or the pink one. Hold them up again, please. Can you fold it in your head? Who thinks the blue one does not make a cube? Put your hands up, please. Ooh, a few hands now. Don't fold it yet. Who thinks the pink one doesn't make a cube? Come on, old people in the middle. Wake up, get with it. There we are. Yes! You try and fold that pink one. Let's see if that makes a cube. This one. Ooh. Well, I'll tell you what, you've done a perfect job. Can I just show people? There we are. Look at that. There you are. Not yet. The thing is, at this one, you think, what's to go on the ends? But what happens is when you first fold it, it goes like that, and there's one more fold, and there we are. You do that one. Then my friend in the middle, he couldn't wait. Do it again for me, mate, because you did it perfectly. Just do it again. It's not your fault. There's nothing you can do about this. Not for want to try, no, is it? Oh, no, this, oh, no. No. Can you show that there's a hole in the end? There we go. Let me hold that up so I can do it perfectly, job. There we are. Thank you, my three volunteers. Thank you, miss. Thank you, and thank you. There you go. Which backs it down? Dear, oh dear. Can't believe that Noah put two of those on the ark. Anyway. Right. What's he doing now? Sorry, I'm just going to get rid of this little funny thing that's turned up. Go away. So I got an email saying, what's your favourite net of a cube? I've got one. How sad's that? I've got a favourite shape that makes it. Would you like to see it? I thought you might, because you're all as daft as I am in this building today. Look at this. Oh, look at that little shape. Now, these little black lines, art lines, are little bits of cotton. And hanging off it, I've got a button. Okay. Sometimes when I'm doing talks and there's very little kids there, like reception class, they don't understand anything. Then they see the button and they're happy. It's the first thing they've understood. I like buttons. I don't know where to lie. I was in this primary school and this little lad put his hand up and said, have you got a question? I like buttons. Thank you for your question. Yes. Then the little girl next to him said, my tummy button came off in the washing machine. What? I just had this image in my head. This little kid's tummy button come and like a balloon going. Anyway, we're going to settle down. We're going to pull the button. Get ready for it now. But when I do this, I'm going to go 1, 2, 3. You've all got to go. Woo! Are you ready? 1, 2, 3. Woo! What's not to like about that? I'll do it again till you clap. Are you ready? 1, 2, 3. Woo! That's the one. There you are. How's that? It's the only one that puts itself together. It's those two, and those two. And that all came from this rather funny email from this kid. Right, what I'm going to show you on here now is this one. It's more for my friends, like a few numbers. But I'm going to explain to you lovely people how you can be mind-bogglingly rich. Write a best-selling book's one of the things. People are loving that. Not all reading them. It gets better. This next one is my favourite. It took hours. How to be rich. What you do is you save the life of the richest person in the universe. He goes, hey, thanks for saving my life. How can I reward you? And because you're a strange mathsy person, you pull a full-size chessboard out of your trouser pocket. You have to wear special trousers. Hey! Okay, like that. Say, right, I want you to come with a chessboard, please, for me, in pound coins. He goes, what, just £1 on every square? And you go, oh, no. £1 on the first square, then 2, then 3, then 4. So every square has got an extra pound coin. Can anybody tell me how many pounds will be on the last square of the chessboard?
This is my 64.
Good lad. Little round of applause. He had his hand up before I asked the question. He's still got his hand up. If you say to me, I like buttons, what are you going to say?
It's impossible.
It's impossible.
I think it's
Go back to buttons. I like buttons. I understood that one. I'll make it possible for you, my friend. Right, the guy says, I don't want to pay all that money because there's £64 there, 63, 62, 61. There's 250 quid on the last 4 squares. He says, can you make it cheaper? You say, okay, never mind pounds, we'll put pennies on the board. But as they're only little pennies, we're not going to go 1, 2, 3, 4, 5, 6. We're going to double them up as we go along. 1, 2, 4, 8, 16. Before we get any older, what's going to make you richer? Pounds or pennies? Hands up for the pounds. Hands up for the pennies. Ooh. See, some of you are instinctively going for the small looking one, but look at the sums. When we get to the end of the first row, on that square there'll be 8 quid. But if you go for the pennies, there's £1.28. In fact, if you add up the money on the first row, you will find that if you go for the pounds, you'll have 36 quid on the first row. If you go for the pennies, you've only got £2.55. And we've already used up the first row. I'm going to ask you again, what makes you richer, the pounds or the pennies? Hands up with the pounds. I'm trying. Hands up for the pennies. Hands up for get on with it. Look at them all down here. Right. There's lovely ways of working this out, triangle numbers and things. But when you've got a nice, clever bunch here, I've cut all that rubbish. We're going to do it by guesswork. Okay? Somebody guesses, I say higher or lower. We're going to guess how many pounds are on the board. With a bit of luck, we should do this in about 10, maybe 12 guesses, unless we get some random guesses. So let's just see how good these kids are. We guess, all I say is higher or lower. Who wants to make the first guess at the number of pounds on the board?
500.
It's more than 500. It's a nice starting guess, though.
Quintillion?
A quintillion. Less than quintillion. Well, at least you've closed the range for it. More than 750.
1,024 pounds.
Ooh, nice guess, but it's more than 1,024.
200.
Did you say 2,000? That is so close, you get a round of applause. Yeah, well done, mate. It's very close to 2,000. Little lad there looking a bit unsure, but that was a very nice guess. It's a bit more than 2,000.
65 times 33 pounds.
It is 65 times 33 pounds or something. Actually, no, it's 65 times 32, but we'll get there in a minute. Let us catch up with you.
2,120.
It's less than 2,100.
2,048.
I'll tell you what, 2048 was so close, I will tell you, 2080, but we got there very quickly, mainly down to that man. Round of applause for the kids getting there. Well done. The guy down there, I've taken it off the PowerPoint for today, but let me explain what's going on. This is a triangle number, okay? There's 64 on the bottom, there's 1 at the top, okay? And if you want to work out the number of items in the triangle number, you take the number at the bottom, multiply by the next number, then you divide by 2. And in fact, you will find that is 65 times 32, which is 2080. That's a very, very quick explanation, but I don't know how he knew that, but I think that is genius. Give that kid a round of applause. Which one was it? Was it you? Yes! Fantastic! And if you'd like to read more about it, there's a very good book called The Murderous Maths of Everything that I wrote. Anyway, there we go. Who wants 2,080 quid? That's enough for 5 iPads. You could stick them along the side of the bath and play Angry Birds right the way along your bathroom wall. Wouldn't that be great? You lie in your bath with your big toe and ping that yellow bird. Woo! Bam! Who wants 5 iPads? Okay, and who's going to turn down 5 iPads and go for the pennies? Some kids have got the bottom. Yeah, I'll take the iPads and the pennies. Let's look at the pennies. There's 1 penny on the first square, 2 on the next square. As we're doubling up, I'm going to write 2 times 2 for the next square. Next square is 2 times 2 times 2. You can see where we're going with this. I won't dwell on it. You can work out how many pennies there are on any square by looking at the square number. That's square number 4. You take away 1, 4 take away 1 is 3, and that's why we've got 3 2s there. 8 take away 1 is 7, that's why we've got 7 2s there. You can work out how many pennies are on any square just by knowing the number of the square. We're going to go to square 19. There is a reason for going to square 19. How many little 2s do I multiply together? Shout out if you know.
18.
The number of pennies on square 19 is 262,144 pennies. If you convert that into pounds, you will see there is actually more money on square 19 than there is on the whole of the board if you convert it in pounds, but only on square 19. What you're about to see sounds like I've made it up just to make my book sell, but it's not. This is the truth. It's just extremely hard to believe. We're going to go to square 21. The number of pennies on square 21, almost exactly 1,000,000 pennies. So what does 1,000,000 pennies look like? If you had a great big bath full of pennies, that's about 1,000,000 pennies. What's a lot more fun though, is if you put your pennies into a tall, thin pile. How high would that pile be? The answer is about 1 mile high. We're only on square 21. We go to square 39. The height of the pile of pennies on square 39 is about as high as the moon. There's more money on square 39 than there is in the whole of the world. But that's nothing, because we're going to go to square 48. We've shot past the moon. The pile of pennies on square 48 is 1.5 times higher than the sun. But if that was your money, if that was loose change rattling around in the bottom of your washing machine, you wouldn't bother fishing it out. Because we are about to go to square 64. Little celebrationary dance there to square 64. Love it. I love it. Keep her going. I'll tell you, great is that. They're not dancing. Look, they just sat there watching. I love the dancers. There we are. The number of pennies on square 64. How many little 2s do I multiply together?
63.
63. Here's what they look like. Somebody said the number of pounds is something like a quintillion, didn't they? Who said that? Well, the number of pennies on square 64 is 9 quintillion, 223 quadrillion, 372 trillion, 36 billion, 854 million, 775,808. Clap! Go on, be honest. First time I did this talk about 2 years ago, I'd learnt that number off by heart. I was at a school in Hull, and this lad put his hand up, and I thought, don't normally get intelligent questions in Hull. I said, have you got a question? Yeah. I said, what's your question? How sad are you? I've been back to that school, I think, 9 times, every year. It's a wonderful school. It's tough as nails, and they're such nice kids as well. There we are. That's the number of pennies on square 64. What do those pennies look like? If you put your pennies on a square on a board, the chances are you probably put them into a cube shape. So how big would that cube be? The answer is it's about 11.5 miles along each side. But that's a bit boring. What's a lot more fun is if you put the pennies into a tall, thin pile. The height of that pile of pennies, we don't measure in kilometres, we don't measure it in miles, we measure it in an astronomical unit of measurement.
Light years?
Yes, 1.5 light years high. Okay. For those of us who get a bit lost in light years, light can travel 1,000,000 miles in 5 seconds. In 5 seconds, light will travel 1,000,000 miles. So how far will light travel in 1.5 years? That's how high that pile of pennies is. It's very hard to paint a mental picture of this. If that pile of pennies started there and went up there, if I turned on a torch now and you were looking up, you wouldn't see the light from the torch until, nearly Christmas 2013. But this is more fun. If I was up there looking down at you people now, it takes 1.5 years for the image of Earth to come up to the top of the pile of pennies. If I was looking at you now, I wouldn't see you sitting there now. I would be watching you people, what you were doing 1.5 years ago. But this is the good bit. I'm going to get a mirror and hold the mirror like that, shining downwards. If you people all got binoculars out with the mirror and looked up at the mirror, 1.5 plus 1.5, you would be watching yourselves live what you were doing 3 years ago. My little friend down here would be at the moment of birth. There we are. Fancy that. There's someone to dance about, baby. So that's how, who thinks that's enough money to be going on with? You're cheating yourselves, you see. That's only the money on square 64. You've also got all the money on the rest of the board. When you add that up, you will find the total number of pennies you've got is 18 quintillion pennies. When you convert it into pounds, you'll never manage to grasp the number of pounds, but there's something lovely at the end that we can all understand. Look, here's how many pounds you get, and look, there's 15p left at the end, ladies and gentlemen. Can we have a round of applause for the pennies on the board? We like doing that. I'm trying to remember what else is on this little song sheet here. Oh, I pushed the wrong button, pardon me. Whoa, that's the one. Let's have a little look. Bam, bam, bam. Oh, I've got to do this trick as well. Let's have a little look here. Nice little one here. This little magic trick involves everybody in the whole room, please. Please don't talk to the person next to you what numbers are going through your head. But can you all start off by thinking of a number in your head between 1 and 9? When you've done it, go, done it. Done it. Can you please add 1 to your number? Done it. Done it. Thank you. Can you please multiply your answer by 9? You might need to do that. Oh, you are quick. Scaring me, this place. Can you? Are the old people doing it? Yes. They'll think, can you all please add 1 to your number? Thank you. And now you should have a 2-digit number in your head. Can you add together the 2 digits of your number? Yeah, you've got that, have you? And finally, listen, if you've got an even number, that's okay. If you've got an odd number, you've gone wrong. Don't panic, you're doing it in your head. I don't know where you are. We should have an even number. Can you please divide your even number by 2? Have you done it? You've got a single digit left. Don't say what letter you get, but turn that single digit into a letter. Have you got a letter? Yes. When I count to 3, shout out the name of an animal that begins with your letter. 1, 2, 3. Elephant. There you are, ladies and gentlemen. How many people said elephant? How many people said eel? Electric eel? Emu? Eagle? Elf? I'll tell you, I was in Liverpool about 2 years ago. So 2 years ago was a funny year for me. I was in Liverpool. I had about 200 kids sitting there. Must have been age, I don't know, probably youngish, 9, I think. And normally I get a few laughs out of kids now. They've been sat there for an hour, laughed, nothing. They stared at me. 200 kids, I put that up. The elephant comes on. 200 kids all went, earthworm. It was really scary. And then the one... I told you about the guy that went, it's turned orange. Remember him? I'm stood there at Manchester Town Hall. It's about 2 weeks before the other kid. Manchester Town Hall. The elephant comes on the board. 999 teenagers go, elephant. And one of them goes, Ewok from Star Wars. So it's lovely that some of you said elephant. That is great. Is that? I'm just looking at the time. I'm whizzing through a couple of little things. We'll do your fortunes and we'll go. Oh, I've not poisoned anybody. I need to poison somebody. This is Murderous Maths for you. I need 3 volunteers to be poisoned. Oh dear. Yes, I want to die. Come on, sweetheart. I'll kill you. I'll kill my lovely friend down here. And who else do I pick? Sorry, let me go over here. Let me pick. You're mad. Sit down. I'll pick this guy here. You come and join me. Thank you very much. I've got 3 volunteers to be poisoned. How are you? Right. Those of you who couldn't say it, this is a very clever little lad who wanted to know more about the binomial theorem. How lovely to see you, friend. You go and stand over there because I'm going to kill him first. Right. This is a funny game. It's called the poison chocolate bar. Pretend that's a bar of chocolate. I know it's Lent. Not real chocolate. Doesn't count. I'm going to poison one square. In fact, you choose which square I poison. So choose any square on there. Just point. Okay. I've poisoned the square. The game is we take turns to basically snap a piece off the chocolate bar. So you might go first and go like that. You've got to go along a line. You might go like that. I might go like that. You might go, I don't know, you might go like that. Okay, but it goes backwards and forwards. The idea is you've got to try and pass me that last piece on its own, and I've got to pass it to you. I'll do the folding. You just tell me where you want me to fold. Do you want to go first or second? He's going second. I'm going to be quite greedy. That's my first go there. Okay, I've taken that whole line down there, and I'm passing that back to you. Now, you show me which line, one of those lines or one of those lines, and I'll fold it. So you choose a line.
Just out of interest, are you going to win?
Actually, I'll tell you what, this is interesting. I don't always win. I have been beaten once. Edinburgh Book Festival 2 years ago, but we don't talk about it. Go on then. I can be beaten. Like that?
Yeah.
I mean, I can be beaten. Basically, I have to wait for him to make a wrong move. And he's already made the wrong move, so I'm feeling quite smug. Right then, there you go. Can you pick any line you like there?
That one. Phone it down.
What, like that?
Yeah.
Is that what you want?
Yeah.
He's gone like that. I've gone like that. Okay. I'm just stand a little bit in there. There's people trying to see from down there. Okay, I've got to there. Pick any of those lines now. What are you going to do? Pick one. You have no chance of living, but thanks for thinking. You take it that one. I'll take that one. No one looking down the back, son. Come on, mate, I've got to move on. Which one? Pick one.
That one.
Well done. You've gone there. I've gone there. You're dead. Give me a round of applause, though. Go sit down. We get acting with some of them as well. You've got the idea of the game now, have you? You get to choose any square you like on there. We'll poison it. That square. Ooh. Right, do you want to go first or second?
Second.
You're going second. Hey? Clever lad. You've gone there. I'm going to go there to start with. Okay, pick a line.
That one.
What, across the top like that?
Yeah.
Is that what you're doing? Oh, heavens above. That's it. I'm going to go like that.
Hold that.
Sorry, that one in there?
Yeah.
He's going to go like that. I'm going to go like that.
Hold that one.
What, like that?
Yeah.
You're going to go like that? There you go, son. Give a round of applause, though. I'll tell you what, he was close. Hello, miss. What I'm going to do now is, the idea is, I can't win until the other person has made a mistake. Of course, the thing is, I do rely on them to make a mistake, and 59 times out of 60, they will. I'm going to play with this lassie now, but as soon as she's made a mistake, and I hope she does, otherwise you're going to kill me, I will try and explain how I win. There are two ways of winning this, but you come and join me. Pick any square you like to be poisoned. That one right in the middle, yeah? Do you want to go first or second?
First.
You want to go first? Okay, you go first. What, like that? Or just the edge one? Can I say, by putting it right in the middle and going first, she's already lost. Whatever she does, she's gone like that. I just copy on the other side. Can you go again, Madani? What, like that? She goes like that. You see it coming? I go like that. What, there?
Yeah.
Okay. It's not good, is it, love? No, it's not. What a feel? Yeah, okay, I'll take it like that. I can't fold the paper anymore. I go like that. Can't even bend it anymore. Look, there you go. That's your turn. You take that one. I'll take that one. You did. Give me a round of applause. Oh, well done, my love. Yeah, there we are. Yeah, there's two ways of doing it. That way, basically, if you can pass it back to them with that bit in the middle, you have to make sure that's there. Go. You copy whatever they do on the other side. There's another way of winning, but that's the easy one. And I don't want to dwell any longer because I need to show you very quickly two more things. That goes there. And we're going to tell you fortunes. 2 and 5, bang. Somewhere it says fortunes. 51. We're going to find out what you people were like the moment you were born. What happens is we take your birthday, I twiddle with the numbers, I turn your birthday into a special number, and then we use those numbers to find out what you like when you were born. I'm going to borrow my lovely, well-behaved, my little friend down there. When was her birthday? What date?
The 9th of October.
9th of October. 1. That's 9th of October. And what year was she?
2008.
2008. I don't use the 20 of 2000, just the 08. I add up the numbers in her birthday. That makes 18, okay? 9 plus 1 plus 8 is 18. I'm looking for a number on that board up there. 18's not there. I keep going. 1 plus 8 equals 9. You're a number 9 down there, my love. I'll do one more over here. Who wants their birthday doing for them down here? Little lassie, right down there. Tell me your birthday, so it's that big voice. Christmas Day, Isaac Newton's birthday. There we are. 2, 5, 1, 2. And what year?
2004.
2004. I added the numbers in your birthday. 7, 8, 9, 10 plus 4 is 14. 14's not there, so 4 plus 1 equals 5. Can all of you who are able to now, please, can you work out your number, a number on that list? You've got about 30 seconds to do it, okay? As many as people as possible. The more that do it, the more fun we have. If there's any small person I can help, I'm very glad to help a small person. Do you want me to work out your one for you? Put your hands up if you've got your birthday number worked out. If you get to 10, by the way, 1 plus 0 equals 1. We've got quite a few people. I'm going to move on now, just to give you a feel of what's going to happen. If you actually got to 1, if your birthday number turned out to be 1, can you put your hand up now, please? Oh, a couple of them down here. Oh, and a couple of the old people. Because look, there we go. 1. Bossy, impulsive, and full of yourself. That's what you were like when you were born. Don't take it personally. Did anybody get a little number? Number that was 2 at the end. Have we got? Oh, a few 2s. You were lovely babies. That gentleman was a lovely baby because you were affectionate, shy, and a deep thinker. Anybody come out as a 3? Oh, loads of 3s. There's 2 parts to this. Read the small print. If you are a 3, party animal, enthusiastic, rather irritating. There we are. Anybody come out as 4? A few 4s. It's possibly the best one in the pack is the 4s. Here we go. Hard working, a good organizer, and cool. Is that how you see yourself? 5. Let's have a little look at number 5s. Any number 5s here? Lady down there, guy at the front. All right, okay. You were 5, weren't you? This is what you were like when you were a baby. Adventurous, restless, and try anything once. Imagine this kid with a full nappy trying anything once. It doesn't bear thinking about. Anybody come out as 6, please? Oh, quite a few 6s. In fact, he's been every number so far. A few 6s. I hope you people are tidy. Are you tidy at home? Gentleman down is a 6. Because, I don't know, you get sensible and domesticated. Yeah, he's nodding, the guy. Yeah, he's a mumsy person. Good lad. Do we have anybody come out as a 7? If you are 7, will you please stand up? Because we love the 7s. 7s, will you please stand up? 7s are a special category of... Oh, there's a whole gaggle of them. If you are 7, be proud. Thank you, the 7s. A round of applause for the 7s. Anybody come out as 8? If you're 8, you're going to be a teacher because you are money-driven and ruthless. That's all there is to it. Now, my little friend down there, my lovely, well-behaved little girl down there is a number 9 down there. Any other number 9s in the room? 9s. This is kind of weird, look. Amazing imagination, rarely look smart. You're hippies. Isn't that great little hippie down there? Occasionally we get an 11. Do bear in mind that this presentation is designed to make school kids giggle. Don't take offence at this. Are you 11?
Yes.
Samuel's 11. Right, it works then. Here we go, look. Artistic, inspiring, and practical. Weirdo. Anyway, right. And finally, does anybody come in at 22? We have a couple of 22s. I'm not surprised in this wonderful place. If you're 22, oh, 2 down here as well. 22. Determined, practical, and you're on a mission to improve the world. Well done, the 22s. Okay. Finally, I wish I had a bit longer, but that's been a delight to talk to you people. Can I just ask before we wind up, how many people here actually live in the Cambridge postcode area? Can you raise your hands? Are you Cambridge people? So a lot of you don't. Anybody come more than 10 miles to be here? Hell, 20, 30, 40, where? New York. Pardon? New York! Give them a round of applause! Oh, I love it! New York! I'd have been all day going 10, 20, 30, 40. Oh, and I'm from Old York, there you go. It was such a great city, we opened another branch. Anyway, fancy that, New York, that's lovely to see you here. Let's have a little look at this thing. I've had a little laugh about the little kids that sit there going, my tummy button and all this sort of stuff. But there's one thing kids in reception class get so right that nobody else gets right. It's this. We're going to put in the diagonals. Now you're just sitting there going, oh yeah, diagonals, you're a star, okay. For little kids, this is magic. They sit there going, oh, star! I think it'd be really nice if you all people just remembered what fun it was to be 4 years old and everything was magic. Go on, get your fingers out. Get your fingers out, all of you. If I see you not joining in, I'll imagine you're saving your energy for a solo at the back. Point at the diagram. Ready? Go. Woo, 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 woo. Don't you feel better for that? And the good news is there's another pentagon in the middle, so we can do it again. Point at it again. Are you ready? Go. I'm going to make the red lines a bit longer. I chop out the triangles. Every year I got a Dublin for Irish Maths Week. I was shown this in a bar, in a Dublin bar at 4 o'clock one morning, and it was just the best trick. Of all the stuff I've shown you, I love this. You make 2 of these. While I'm putting this together with a great big elastic band, can I really thank the lovely... Where are you, Sarah? Is she there? She's there with the camera. Sarah's dug me out again and invited me back. It's probably my favourite gig coming here because I can tell people I've done the Isaac Newton Institute. Will you give a bit of love for Sarah there at the back? Thank you, my love. Great to be here. Anyway, I get the elastic band, I put it round all the edges. No, honestly, you see my CV of where I travelled to. I do sort of all sorts of kind of schools and rough old gigs and festivals. But this one, my mum's ever so proud. Always wanted me to go to Cambridge. Here I am. There we go. What's not to like about that? Be honest with you. All right, thank you all of you. Take care of yourselves. It's been a delight. Right. Hiya, Chrissy, you got another speech to make? Go on, girl.
Thank you so much for saying nothing more than that was just wonderful, inspiring and exciting. So thank you very much. And thank you to all of you.
Take care, all of you.
And the final thing. Wonderful red balloons in the foyer saying, "We love maths."